Our next speaker is Nagore Ortiz, and she comes from the EnergiGUNE, EnergiGUNE, sorry. And she holds a Iker Basque grant, and she's working on batteries, she told me, but she will explain us better that point.
Thank you for the introduction and good afternoon, everyone. I would like first to thank the organizer and especially Eugenio for the invitation. So now we will change the thematic and I will talk about electrochemical energy storage, what we do at CIC EnergiGUNE, which is a research institution in the north of Spain in the Basque Country. So first, I will give a general overview of energy storage and what is going on at the European level, then to focus on the batteries and a short introduction for those who are not familiar with this, with electrochemistry, and at the end, beyond lithium-ion batteries and the case of metal batteries, which is the batteries I work on. So first, energy storage is key towards decarbonization. And why do we need energy storage? Because more and more we all have in our mobiles, more in our cars, buses, and all the appliances we have at home. So this is becoming really, really important in this present scenario. And what we are doing at the European level. So at the European level, we have this Europe Energy Roadmap 2050, what the purpose and the goal is to reduce its emissions by 80 to 90% by 2050, and by 2030, just in 8 years, by around 45 to 50%. So this means that we want to go near neutral at the European level, and for that we have different technologies at different routes that we can take. This was signed in the, I don't know if you know, the European Green Deal. That was a commitment at the European level for the future generation. And in the 2030, as I say, to reduce the greenhouse gas emissions by at least 50%. So in this scenario, energy storage has become a key enabling technology for the efficient and secure integration of the renewable energy. To have this integrated at the sector level and to have energy cost efficiently and to provide them to the different sectors. So we know that we have the supply, the solar and wind energy, but we also know that we have this load and this is the supply, but there are sometimes at the day that energy is wasted. So how we are going to store that energy? There are different storage systems, and I will talk briefly at the different electrical, and then I will just focus on the electrochemical energy storage. We can store in the chemical fields, in fuel cells, electrolysis, or this morning the talk on hydrogen and the batteries, which I will focus on this. This is for you to know and to understand the system energy storage. We can store energy in various forms: mechanical, thermal, chemical, electrochemical, and electrical. For you to give you an explanation of a difference between what is a battery and what is a capacitor. So in a battery, we store the energy of with an electrochemical reaction. This is a redox process, and it's a chemical process, so it's a slow process. In a capacitor, it's totally different. It's based on the absorption of the charges at the two electrodes. And this is a physical process which is fast. So for you to better understand, we have this really nice example. For example, in the batteries, we have when the PC is operating, we are using the battery, and this would be like a marathon runner that you really long energy for a long time. But when we are talking about capacitors, they have high power density. So this means we have in our computers normally to switch on this capacitor, and this would be like a sprinter. So now I will focus on batteries. So batteries have evolved really fast, contributing to the increasing energy demand, and we need high energy and high power energy density batteries. I will first talk about lithium ion batteries that they are known and commercialized since the 1990 and have satisfied many of the demands that we have. But this, I will explain you why these batteries, they are limited by the chemistry, which is based on the intercalation. So now in the recent years, there has been a focus on looking and researching beyond lithium ion batteries. So here you can see a Ragon plot looking at different electrochemical energy storage technologies. As I explained you before in this, we have here the power, here the energy density, high power density, we have the capacitors, high energy density, we have fuel cells and different kind of batteries. Here I will talk about lithium ion, and then I will move in this zone to talk about metal batteries. So for you to understand this increasing demand at the European level, there has been recently an initiative in the past few years called the Battery 2030 towards this chemistry neutral approach that I explained before. And this is focused at different level. First, we have different projects on artificial intelligence for the discovery of the materials. There are many, many materials that can work in a battery, but we cannot try them all at the experimental level. So first we need to focus on the computational to get insight, so then we can work at the level. We also have a lot of sensing of self-healing that is really important for a battery. For example, if you have a solid electrolyte and it's squeezed and then you want to revert and that property. And also really, really important life cycle recyclability. That's it. So in this sense, we have different batteries. We are now here in the lithium battery chemistry in the generation 3, and we are started at the generation 4 that they are all solid state batteries. And also generation 5, which I will talk is the upcoming generation of metal or metal sulfur batteries. And I'm sure you have seen on the TV that there are a lot of European gigafactories, and in Spain they are different, that they are going, at least they are meant to be, we have one in the Basque Country, another in Valencia, in order to meet of this energy demand. So just briefly, I talk about what is battery. Today I will focus for you sometimes we call primary and secondary batteries. Primary, they are those that they are not rechargeable, and today I will talk about secondary batteries, that they are those that they are rechargeable. So here, as I said, this is, for example, the battery we all have in our mobile phones, that it was first commercialized by Sony in 1990. And this is the configuration. So in a battery, we have an anode. In this case, this anode is based on graphite. Then we have a conducting electrolyte. In this case, and in the ones commercially, is an organic electrolyte. And then we have the cathode. So for this, you can see that all the materials that we are going to use for lithium-ion batteries, they are really open structured when we can intercalate the material. Because here, in the graphite, what happens is intercalation of lithium ions for this cathode, which is lithium cobalt oxide, and they are going when we charge to one side, and when we recharge, this process is irreversible. So here in these batteries, we are going to be limited by how many of these lithium cations we can store in the materials. So normally we are talking about capacity of around 300, 400 milliamp hours. And also now there is an interest of move towards cobalt and other critical raw materials. That's the reason we are still looking for new materials. And this, I guess you know, the Nobel Prize in 2019 was for the discovery of the lithium-ion battery. And we have here the three men involved in this discovery. So first we have Whittingham, who discovered that lithium can be a really good anode because it was easily oxidized and release the electrons. Then we have Goodenough that discovered the cathode materials that can store energy, and also Josina's contribution was to the anode, that we don't need lithium, but we can use carbon materials such as graphite to use it as the anode. And here you have the story first about the solid state batteries. Now there is, we are looking to move from the liquid to the solid state electrolytes because you are safer. I know many of you have shown or on the news that maybe a battery explode. This is because we are using an organic electrolyte that is liquid, there is heat, and that heat can provoke this to explode. So moving to solid state electrolyte is the current scenario, but back in 1972, Michel Armand already discovered this solid state battery that was based on a gel polymer electrolyte and on a metal. And we can see that there are some vehicles and buses that they use these batteries. And in the case of the lithium ion, we have seen many materials going from perovskite to spinels, but all with this open structure, we can accommodate these changes of intercalation, the intercalation of the lithium cations. So here is a summary of the main electromaterials. We use it in batteries for you to understand. We have what I talked about until now is the insertion materials, that they are the usual process, but they have low capacity. Low capacity because normally they are limited but one electron, because it's lithium, what is moving from one side to another. Then we have the alloying, that we have some commercialized, they have very large capacity, but in this one, for example, in that they are used for the anode, we need to alloy the metal with the lithium. So there are many challenges to accommodate all the volume changes that this anode must comprise. And then the conversion reactions that they are still at the development, such as metal air batteries that I will discuss later. And this is based in a totally new material. So we have a cation and we have another in metal air and oxide, and we are producing a new oxide or a new compound where the energy is stored. So now I will move to beyond lithium ion batteries. As I said, lithium ion batteries, they are the ones commercialized, but we need more energy storage technologies in order to meet the current demand. And here we can see that when we are looking for high energy density, we are looking, or we are going to metal oxygen or air batteries. It can be the applications to electric vehicles or grid energy storage. We also have another metal ion batteries that can be also applied to both stationary and mobile applications. And this is a nice figure when we can see all the cations. First, the battery started with lithium ion. We all have sodium, potassium, that this is one electron process. If we want to complicate our lives maybe a bit more, we are going to two electron process, that these ones are at the development, but this will have double the energy of one electron transfer. And this, the new technology, will have the oxygen batteries and the metal sulfur batteries. So in the case of the metal air batteries, the configuration is very similar to the lithium ion batteries. We have an anode, normally a metallic anode, but we can use other negative electrodes. Really important, and what I will talk about is about the air cathode, where the oxygen is diffused and is reduced. So here we need an electronic conductor, and I will talk about graphene, because these systems, they are open to air. This is a battery where the oxygen is the fuel. And then we also have the electrolyte. As I said, we can have liquid and solid electrolytes. And also in this kind of batteries, we can have aqueous electrolyte and non-aqueous electrolyte. And today, now I will focus on sodium oxygen batteries. So in this kind of batteries, we have a sodium metal and sodium conducting electrolyte and an air cathode. So what is happening during this charge? We have oxygen that is reduced on the surface of the cathode, and the sodium is oxidized. And then they are combined to form, in principle, this kind of oxide when the energy is stored. So when we discharge, we form this. This is sodium superoxide on the surface of the carbon cathode, and this is where the energy is stored. And this reaction is reversible upon charge. So here you can see this is a typical discharge plot for metal air batteries. So in here, as I said, this is a conversion reaction. So we are not moving the ions, but we are forming oxides. And in the case of the lithium air, we have lithium peroxide. And as we go here depth on the capacity, we can see that these discharge products grow. So here, first we have the first step, we can see here that is the nucleation, where we are nucleating on the surface of the carbon electrode, these small particles. Then the flat plateau is when these particles outgrow, and the longer, the higher this plateau, the higher would be the capacity and the better our battery would be, until it reaches a saturation point. This is where all the cathode is going to become clogged with these particles, and the battery is going to die. So for that is really important. The so-called triple phase boundary is where this reaction is happening at the air electrode, is with the solid, which is the cathode, the liquid, and the gas mean. And here we have been working with different carbon materials. The first paper, it was from 2012 from a German group where they used carbon paper. And then later we were using also carbon nanotubes. As you can see here, you can accommodate better all of these. They are all the discharge products. So this one had higher discharge capacity. And lately, we've been focused here. There are all the requirements that we need for this, as I have explained, for the oxygen reduction and evolution reaction, a really high surface area to accommodate all the discharge products, the electron transfer really important, and for that carbon materials, they are a great choice. So we've been focusing the last 4 or 5 years looking at graphene-based materials. We have, there's been several talks on graphene. They have very nice properties, but then for the production and the electrical applications, what we're using is reduced graphene sheets, where we have these defects, and in these defects is with the oxygen reduction and evolution reactions going to take place. But in these materials, when you are processing the graphene, what is happening is restacking. And for that, this is not good for our application, because we need a really open structure to accommodate all these discharge products. So we've been focused on 3D reduced graphene oxides to prevent this sheet restacking by freeze drying, where we can accommodate as much discharge product as we can. So the first work that we conducted was to study the porosity. And as I say, graphene has high surface area, chemical stability, and electronic conductivity. So what we did is to produce 3D structures. This is for common Hammer's method. So what we did is three different graphene electrodes, one like 2D with not three-dimensional in nature, just a film. Then we were increasing the mesoporosity by different freeze drying temperatures. And we have seen that in this case, increasing the mesoporosity, we increase the performance. Here we have the discharge, and we can see that the higher the mesoporosity, the higher the discharge capacity. So for these batteries, the porosity and the mesoporosity is very important. Why? Because when we have a film, the diffusion of oxygen is hindered. So we just have the diffusion on top of the cathode surface, so when the reactions are going to happen. But when we increase the mesoporosity, we have the diffusion of oxygen that can go into the graphene sheets, and the oxygen reduction can happen in those sheets. And that is enhanced for the one with higher mesoporosity. And here also you can see really nicely how the sodium superoxide cubes grow, that in the one that has higher mesoporosity, all the surface is used. That's the reason it has higher discharge capacity. And also when you go to cycle this battery, the cycle number is also higher. So the critical parameters, we determined that it was that mesosmall macro pulse in this range, and also the random orientation of the graphene sheet. So another example that, that we studied was to compare the currently used, this is carbon paper, normally used in fuel cells. It's a carbon electrode, and on the top a gas diffusion layer that is porous carbon with binder. Then we have this reduced graphene oxide that in this case was from Graphene, commercial, and then we reduce, and then we freeze dries to produce aerogels. And then we have electrochemical exfoliated graphene. So in this one, we also saw that looking at the different, all have a mesoporous nature, but in the case of the EEG, the BT surface area was higher, and also a higher structural order. That was really important to accommodate all this discharge product and to have higher discharge capacity. But for this work, what we did is to use X-ray diffraction to quantify this discharge, the efficiency of this discharge product. So what we did is discharge a sodium oxygen battery electrode, and then with an internal reference, we can quantify how much sodium superoxide we have in our cell, depending on the cathode we were using. And well, I'm not going to explain today because on Thursday there are another 2 examples looking at graphene. Lydia will present the perfluorinated binders in graphene-based sodium oxygen battery, how using BTFE we can modulate this triple phase boundary and enhance the performance of these batteries. And Arancha will present the boosting the performance of graphene by using small biomolecules. In this work, what we did is we have a graphene, and on top of the graphene, we have these small biomolecules that they are catalyzing the oxygen reduction and evolution reactions. So for a battery or for to become real a commercial, there are lots of steps to carry. First, we need to work at the materials development. I haven't talked about the anode, but it's really important if we want to use, and that is the reason we are moving through solid state batteries using, and I'm sure you heard about lithium metal, we need to protect because it's really flammable with air. We also need to work on the different electrolytes, the cathode materials that I talked today, and then understanding the mechanisms at the nanoscale, for example, what is happening at the different interfaces, and also what is happening at the cell and then at the battery pack. So finally, I would like to thank all the members on the Metal Air Research line at CAC EnergiGUNE, and also all the funding agencies for the support, and thank you for your attention.
Now there's time for questions. Sorry.
Thank you very much for the talk. I would like to ask, how important is the porosity in your case for the examples you saw? Regarding the porosity, how important is the surface area, for example, of the materials you use?
It's important to have not that to have high surface area, but to have this randomly oriented seed, because even if you have, for example, that perovskite materials that can have really high surface area, but then if they're like the freenas I saw, if they're like in just 2D or they have this random orientation, these batteries, they're not working. So it's a combination of how this is ordered.
No, about the orientation, yeah. Then if you have the layers in this direction, you have problems, but if you have in perpendicular direction, can be better or not? Then there are some materials in which, with graphene, for example, people are trying, or with other materials, to orient inside also the layers to make systems that can have better performance, having an internal order in the material.
Yeah, the idea is to have but not just one order. You have different ordering because the most important or the critical parameter is the oxygen diffusion. So if they are all ordered in the same way, the diffusion of oxygen is hindered within the cathode, because we need to, then the reaction is happening at the cathode interface at electrolyte. So you need different orientation.
Okay, then, well, you didn't talk about also systems that you are making, well, in the institute you are making, that are the systems that are hybrids between batteries and supercapacitors. Then which is the advantage of using these ones?
Well, in those cases, we are combining the, as I said before, the power density with the energy density. So then we have not just for this application that you have really high energy density, that sometimes we also need the power. So those they are for certain applications. So we have batteries, and in the case of metal air, that can be used for stationary applications because you need the energy, but if you need the power, you have capacitor. And then we are working on this hybrid that also we are working on. I'm not working on those hybrids, but there is a research line dedicated to that, working on graphene, on mesoporous carbons, and for that.
No, because, well, I mean, from the point of view of the performance, it's clear that if you have a hybrid, you will have the combination of both things.
Both, yes.
And then what I understand a little also is if you have this kind of systems, you are removing a little more the lithium in your system, or, well, you have less dependence with respect to some metals, and you are using more carbon.
Yeah, of course, because then you have two carbons electrodes, and one is doing intercalation and the other is a physics process where the charges are stored.
Then from the materials point of view is, well, we are more here interested in the materials. I think that the materials is what make the systems more safe, because the lithium is less safe, and perhaps these systems can be good for are less heavy, I suppose, and also they have no problems with instability and explosions or whatever you can have in.
Yeah, that's the reason we are moving from the, as I say, from the liquid, I haven't explained the electrolyte, to solid electrolytes and polymers, ceramic, and hybrid polymer ceramic electrolytes also.
And with respect to the sodium batteries, which is the state of the art? People are always claiming that we will have sodium batteries, but at the end, sodium batteries are not in the market.
Well, not yet, because it takes, so I explained, like, since Wittingham started in the 70s until the 90s, that Sony commercialized, it was 20 years. Sodium batteries, they were started at the center of the lithium ion, but then they stopped when lithium ion got commercialized, and then we started back in, I don't know, 10 years or 10 years ago. So still they are now, the proof of concept at lab scale is done. So now is the step we are at the prototype level. And at CIC, we are now on the prototype. We have selected the materials. So for you to understand, so we need at least, I don't know, 10 years or more just to develop the materials. And then the materials, they work really nice at the smallest scale. So we are working at coin cells, but then when we need to work at a pouch cell that will have 5-10 centimeters, that there is the challenge. So the materials, they are already there. They are based on layer oxide. There is also Prussian brew. There is a Swedish company that is starting was a spin-off from Uppsala University and started to make this material. So I hope in the coming years, we will also see sodium ion, but more, I guess, for stationary or those applications that then not require higher energy density, because sodium ion has less energy than lithium ion. So.
Okay. Then more questions, or, well, you can. Thank you, Nagore.